Hello everyone, this is John Buck. I'm back with another discrete time linear systems video. In this video we're going to talk about first order systems, and then there's a follow-on video about second order systems. First and second order systems are fundamental building blocks, and so we're going to really dig in deeply to understand how they behave both in the time domain and the frequency domain, and how those two behaviors are linked. One of the reasons they're important is if I have a large higher order system with real valued coefficients, I can always factor it and decompose it into either a cascade or a parallel combination of first and second order systems with real coefficients themselves. So we do want to get to know these well. Another reason it's good to get to know these well is often in practical engineering problems, you just need some filtering. You don't need a really ideal filter. And so we'll see that first and second order systems are basic, can act as basic low pass, high pass, or band pass filters depending on the coefficients we choose, and they're much more computationally efficient than some of the longer FIR filters we've just seen last week in class. So there are times where you don't need a perfect or almost perfect filter. Just ability filtering is good enough for your project, and so understanding these well and when you can use them to save resources like time or power or silicon in hardware is a good engineering practice to have. So let's switch to the whiteboard and get started. Okay, so again, today's topic is first order systems. And looking at, again, a very simple equation for first order system. This is sort of the prototype of it. We know this is first order, right? Because we say to find the order of an LTI system, we look for the biggest delay in the system. And so this has, a delay, well, no delay here, and a delay of 1. So again, just to remind us, the delay of 1 means first order. So that's the largest delay in the system. Another thing that's worth pointing out, because it's a tricky little detail, but it matters, is the way we've written this is as minus a. The sign of a, we'll see, has important, understand that this is minus a, has important properties for how the system behaves. And so the first thing we want to do is say, well, for this generic first order system, we can solve in the generic form for just any parameter a here. We want to find the Fourier, the frequency response. So to find the frequency response, we start by taking the Fourier transform of both sides of the equation. And so the y of n becomes yv to the j omega. The delayed and scaled version of y of n gets multiplied by a complex exponential. And then x of n, Fourier transform, is x of e to the j omega. And now to solve for the frequency response h of e to the j omega is the ratio of the output Fourier transform, y of e to the j omega, divided by the input Fourier transform, x of e to the j omega. And when I do that, I divide both sides and factor things out. We've done a bunch like this, so I'm going to just cut to the chase here. It's 1 over 1 minus a e to the minus j omega. Right, so this is my frequency response. And we'll see in a minute, when we look at the magnitude of this, how it looks in frequency. But before we do that, we're going to talk about what's the impulse response of the system. Just to practice your Fourier skills a little bit, and pause the video here in just a second and try to remember yourself what h of n is for this Fourier transform. And then when we come back, we can go through it. So just pause now for a sec. Okay, and we're back. And this is a common one we've seen a lot of. It's minus a of e to the j omega in the denominator. The impulse response is a to the n u of n. And so if I were going to sort of sketch a notional version of that, the u of n means that this is negative up until time 0. When n equals 0, a to the 0 will be 1. And then after that, it's going to be decaying down, something like this. Now, in drawing it this way, this is my sort of cartoon sketch. It'll be 1 and then a and a squared, a cubed for the amplitude, and so on. I've made an assumption about a in drawing it this way. So again, remind yourself what that is, or if you need to think for a minute, pause the video and try to remember what this assumes about a. Okay, we're back. What this assumes is in drawing it this way, I've assumed that a is a positive number but less than 1. Right? It's less than 1 because things are decaying off exponentially. It's positive because all the values here are positive. If a were less than 1, I'd see things oscillating up and down, right? So I can also have a first order system, and we'll see examples of this shortly, that might look more like this, where it would still be 1 at time 0, but then the next value would be down here. Well, if a is a negative number, it would be down here, and then back up here, and then down here, and up here, right? So it would be dying off, but it would be switching signs for every other sample. Like the even numbered samples would be positive, the odd numbered samples, the odd indexed samples would be negative, right? And so this is what I would see if the magnitude of a is less than 1, but it's a negative number, so something like -1/2 or -3/4. Two things, knowing these are LTI systems, we can observe about both of these the way they're drawn, right? So we can say, well, the way I've drawn these, I'm assuming it's also a causal system, because the impulse response is 0 for n less than 0, and I'm assuming it's a stable system, right? Because with a less than magnitude of a less than 1, we can say I could take the sum as n goes from 0 to infinity of alpha of n. It would be 1 over 1 minus a, which is less than infinity. So this again assumes we have a stable system here for the LTI part. Okay, so those are, and we'll see some examples of those in a second. One other thing I thought I would mention, because it does come up, in addition to the impulse response when we think about first order systems, is the step response. And if I think about the step response of a system, the impulse response says what happens when I put delta of n in. In a lot of practical engineering systems, I may put in an input that's a step response or some kind of step. For example, I may tell a robot arm to move from the angle you're at now to a new angle. That's the input, is saying jump to this position. Well, the arm is going to move there, and if h of n is the impulse response of the system's mechanical properties, the step response, what I get when I convolve h of n with u of n, is going to tell me how the system behaves for a step. Another example of that could be the cruise control of your car, right? The input to the system in that case would be where I set the accelerator or the speed I set it at. And if I've just changed the speed either up or down, and h of n is the impulse response of the sort of the car's dynamics, then s of n is going to tell me how am I going to get from the speed I'm at now to that new speed that you've just changed with the step, how this overall car will respond. And we'd like that to be smooth, not too fast, but not too slow. And so those are practical places where we care about the step response. So in this case, again, we've seen the impulse response, h of n, is u of n. We convolve this with u of n. I'm not going to go through all the steps now because they are in the book, but the important idea is using a finite geometric series, we'll find that I can write this as 1 minus a to the n over 1 minus a. And again, the key idea in solving that is to use the finite geometric series. I can also write this in a useful form if I just break it into a sum of two pieces, or difference of two pieces, based on the numerator. Right? And then what this is saying is as n goes to infinity, again, assuming a is less than 1, right, this is a transient that dies out, and this is my steady state. So if I tell the system to take a jump, it's going to end up eventually at this new constant value of 1 over 1 minus a, but along the way I'm going to have this thing die out. So what that will look like if I sort of, we're not going to do it in STEM style, but it would basically go up and then level off like this, as we often saw in RC circuits. And this final asymptote would be 1 over 1 minus a. And how long it takes to get there depends on the value of a. Right? For a small a, like a tenth or a hundredth, this would die off very quickly, and I'd almost slam up there. If a is just barely less than 1, this is going to take a long time to die off, and it might be much broader. Okay, so that's some basic ideas on first order systems and step response. I'm going to, in a minute, then I'll start a new video actually for first order system examples. I'll show you some what this looks like with some actual values plugged in.